Okay, I hope that's clear enough for you. I've made some changes and additions to reflect the actual exact circuit that I'm using. Uh, and so uh, these LEDs are out of the circuit, and I've just bridged across there so that you can ignore that part. Here is the actual choke that I'm using for the inductor. The component values are all listed. So there's one LED on the secondary winding of the inductor, and there's one LED across in parallel with the primary winding of the inductor. And this is actually a one-to-one choke. So there are, even though it's not shown that way, there are the same number of windings in both of the windings of that inductor. Okay, so scope channel, I'm monitoring across where the battery is, and when I remove one battery, I'm removing it right there. So the scope is still monitoring across where the battery would be hooked up. This scope channel I'm not using. I'm using the other scope channel to monitor the output of the F43 function generator. And when I put the capacitor in, the capacitor will be right there. It'll be in series with the positive output of the function generator, just like I said, and like Rosemary can't seem to understand. I'm using two N7000 MOSFETs. There's the pinout of the MOSFET, and these MOSFETs do indeed have an internal body diode, just like most MOSFETs do. It's just not normally shown on the diagram of the two N7000. These diodes, of course, should be inside the MOSFET symbol. They're not separate components on the board. Alright? That's the circuit. And there's the instantiation of it. Now, I've not hooked up, there's the little capacitor, and so I'll be hooking up either directly, as I have been, or through the capacitor with the output of the function generator. The function generator is set to produce a square wave at 1 kilohertz. Alright? And there's where the baselines are on the oscilloscope. Channel A baseline right there, and channel B baseline, and there we're seeing that 60 hertz hum. Let me just turn it off. There you go. So there's where the channel B, let me adjust that a little bit. Scope is still kind of warming up. Okay, so there's where your baselines are, A and B. So turn that on. So there's the output from the signal generator under no load, and I have it set at 10 volts peak to peak, or 10 volts per division, sorry. So you're seeing from the baseline there, you're seeing plus or minus 10 volts. Now I can vary that. With this function generator no load, it'll go up to about 40 volts peak to peak, but we'll start with it at 10 volts peak to peak. Now I can also vary the offset, the DC offset, by pulling this knob and turning it, and that has this effect. And if I push it in, it goes back to 0 offset, so that we're plus or minus. If I pull it out and turn it, I can go to where the signal is all positive or all negative, 0 to negative 20 volts, 0 to positive 20 volts, or the normal 0 offset right there. Okay, so now with the scope probe monitoring across the battery pack, but with the battery disconnected, I'll hook up the function generator to the circuit without the capacitor in series. Okay, and you can see what happens there is that the oh, sorry, I don't have the channel turned on. So both channels are turned on now. This little fluctuation is that 60 hertz hum that the thing is picking up from the line. If I go to line triggering, you can see that stabilizes out. So that's the hum from the line. That'll go away when I start actually hooking things up. So now I'm going to hook up the function generator without the capacitor in the circuit, right there, and you see that output. The B channel is 1 volt per division. So there's your output. You can see how the output of the function generator has dropped because the circuit is loading up the function generator, and the generator can't produce stable output voltage with that much on it. It produces a stable output voltage, just not at the correct amplitude. The most I can get out of it is about 8 volts peak to peak. But as I increase the amplitude, you can see that the response of the circuit, this B trace, right, the square wave reflects what's being put in, and when I go to sufficient amplitude to really get those MOSFETs going, you see that feedback oscillation on the tops and the bottoms of the output trace. Now if I change the offset, I can move that feedback to where it's all on the top, that is when the MOSFETs are on, or it's all on the bottom, switching the other MOSFET on with the negative side of the applied pulse. Alright. So, but with offset set to 0, I think both MOSFETs are switching, since I'm swinging positive and negative 8 volts. And so you're seeing that feedback oscillation on top of both parts of the signal. Now, if I put the battery in the circuit, what happens is the battery voltage shows up at plus 3 volts, and then those oscillations are superimposed on top of that. And now if I change the offset here, I can change the phase of those oscillations and make them go from basically from one MOSFET being switched to the other MOSFET. Okay, and I hope that it's clear by now that these are the same oscillations in form and behavior as the oscillations that are being shown in the Rosemary video from last year. Okay, they're just the same. They even have the same frequency. If I break this down, this oscilloscope is it's very difficult to show very high frequencies on this oscilloscope. It has a low bandwidth, but the frequency of that oscillation is in the 1 to 1.5 megahertz range. Pretty much the same as the oscillations that Rosemary has showed. They quoted 1.2 megahertz. Okay, what I'm doing there is just varying the offset up and down. All right, now let's take the battery out again. Oh, I wanted to show, oh, wait a minute. Okay, wait, let's take the battery out again. I'm getting ahead of myself here. And I'm only using one hand. So there's that bit. Let's turn it so that it's just on the top. Well, let's just leave it like it is. All right, so there's all of that feedback oscillation on the top and the bottom without the battery in the circuit. Now I'm going to move the function generator to the other side of the capacitor. So now we're feeding through the capacitor. Alright, and here, let me just do that for you. So there's without the capacitor, and there's through the capacitor. Okay, so that's the B trace. Move it a little bit. So you can see that the function generator's square wave is passed through the capacitor with a little bit of distortion. But you can also see that that oscillation's gone away, and that the function generator's output is no longer being loaded down. There, see how narrow that is? And then over here it goes back up. Alright, and I can vary the offset of the function generator, and when I get really, really negative, the MOSFETs start not switching anymore down there. And then if I reduce the power of the function generator, you get to a point where you also don't see that reflected on the output. Alright, so now when I put the battery in, I get the straight 3 volt battery voltage up there. I've actually just moved the baseline a little bit. Let me get that back, sorry. There's the baseline. So there's 1, 2, 3 volts of the output without the oscillation that we were seeing before superimposed on there, and then as I vary the offset. Okay, now the behavior of the LEDs is very interesting. Let me go back to the feedback setup there. Okay, so there's, with the battery in, there's that. Now I think you can see that one LED is lit, right? And if I get this right, so now I'm going to vary that offset again. One LED goes out, there they're both lit. Okay, let me find a place where they're both lit like that. Okay. So what I've done is I've just varied the offset, and now you can see that we have this what Rosemary calls a robust continuous oscillation up there. And so that LED is lit. So what I'm going to do now is I'm just going to unplug that LED and turn it around. This is the one, this one here is the one on the primary, across the primary, okay? So what I'm going to do here is just take that out, and I'm going to turn it around, and I'm going to put it back in. If I can get it in the holes. I think you can see that it is glowing brilliantly in that direction. Alright, and that one is still on a little bit too. Okay, so now let me vary that offset again, and you can see that that LED brightens and dims as I vary the offset. Go back to 0 offset there. Now the LED is, well, wait a minute, let me find a place where they're actually both glowing again. There we go. Okay. Now once again, I'm going to take that LED out, turn it around, and put it back in. I've got too many things in the holes there. And you can see that it's glowing now in that direction as well. So this LED, or the current flow right here, can actually be in both directions. We would be lighting up 2 back-to-back LEDs there. But that's an effect of the inductor. The inductor is actually causing that to happen. If I take the inductor out, it doesn't happen. But I still get these oscillations. The oscillations are not a result of the inductance. I can just pull that inductor out like that, and it has no effect on the behavior of the circuit. Changing the offset here. Alright, let me put the inductor back in. There. Okay, my LED's back on yet? It would have on. There we go, there's both LEDs on by putting the offset in just the right place. And then, once again, I'll take this one out, turn it around, and put it back in, same place. And there, you can see it glowing. Get it in the holes. There. Take it out, turn it around, and plug it back in the first way. I'm overloading my breadboard here. I don't have enough holes. Alright, that's it. Thanks for watching.